Alright, now let's talk about domain and range a little bit. And really, I think we're going to talk more about domain here. We're not going to really get into the range, too much on these questions. So just ignore the range part, because we haven't really gotten into that much. So just determine the domain here. So we've got f of x and g of x. What's f of g? Now notice what's different about this question. There's no x value that we're plugging in. This is just f of g. You can think of this as saying, what's f of g of just x in general? Not a specific value for x. We're just leaving that variable there. So by our definition, that's still f of g of x. Okay, which means we're going to do f of, what's our g of x? That's 2x plus 3, right? G of x right here. And then if we do f of that, that's taking a 2x plus 3, and that's plugging it into these x's right here, into that f function, right? So that's going to look like 2x plus 3 squared plus 3 times 2x plus 3 minus 1. So all the x's get replaced with a 2x plus 3. And now we need to simplify that down. So if you square a 2x plus 3, that's like doing FOIL, right? So you would FOIL all that out. And just trust me here on the answer. That's going to be a 4x squared plus 12x plus 9. We can also distribute that 3. So plus 6x plus 9 minus 1. And then combine all of our like terms. 4x squared, a 12x and a 6x make an 18x. 9 and 9 is 18, minus 1 is 17. So 4x squared plus 18x plus 17 is f of g. Okay, this is f of g of x. Okay, the other part, again, what's the domain? Well, that's a polynomial function. So the domain is, for a polynomial, it's all real numbers. So that's that. Now we're going to switch it around and do g of f. So reversing these now the g is on the outside and the x is on the inside. I'm sorry, the f is on the inside. So this is g of, now f of x is x squared plus 3x minus 1. So we always replace the inside function first. And now if we plug this, x squared plus 3x minus 1, into the g function, remember g is 2x plus 3, so that's 2 times x squared plus 3x minus 1 plus 3. This one's not quite as bad as that last one. We can just distribute 2x squared plus 6x minus 2, and then combine those two together and get 2x squared plus 6x plus 1. So that's our final answer. So g of f. And again, that's a polynomial, so the domain is all real numbers again. And those are infinities. pretty sloppy. Let me fix that. Okay, good enough. Now let's talk a little bit more about finding the domain of the composite function. For those two that we just worked with, the domains were all real numbers. You know, we were working with polynomials all the way across, so nothing too tricky about that. If you're dealing with polynomials, all real numbers for the domain is pretty much the standard result. But that's not always what we work with. Sometimes we have rational functions and other things, and so we got a couple of things to keep in mind when we're finding the domain of a composite function. And so the first thing we got to keep in mind is it goes back to this picture. Okay, this picture I drew, not the oil one, this one right here. Okay, where we're chaining these functions together. So when we take an x value, because remember the domain is dealing with x values that can work in the function. So if we're dealing with a composite function, then when we think about the x values that work, notice what happens to that x value. When you plug an x value into that composite function, it goes into that g of x function first, right? So what that tells us about the domain is, okay, right off the bat, if that g of x function is where x goes first, if there's any x values that don't work in g of x, they don't work in the composite function. Okay, let me say that again. If there's any x values that don't work in g of x, that's the inside function, okay, whatever function is on the inside, any x values that don't work there do not work in the composite function. Okay. And so with that in mind, and that's what this first note here says, any values that excluded from the domain of g of x must also be excluded from the domain of the composite. So if it doesn't work in the inside function, okay, it's not always strictly g of x. We're referring to the g of x as the inside function here. If it doesn't work in that inside function, it doesn't work in the composite function. So with that in mind, let's kind of start on this next example. It says find the domain of the composite function f of g. So we're looking at f of g of x, which again is that definition there. Now, what's our inside function? That's g of x. Okay. So the first thing we need to decide is, are there any values that don't work in the inside function? Okay. So for g of x, x can't be positive 1, right? Because of this denominator. So, you know, that means when we talk about the domain, we already know that x can't be 1, okay? Because that's what the inside function says. Now, let's kind of keep working and actually figure out what f of g is. And there's another part to the domain we need to look at here in just a second. So let's continue working this down here and find out what f of g looks like. G of x is 4 over x minus 1. And then if we plug this into f, we get something that looks like this. Okay, so that's kind of a mess, but we can actually simplify that down. The way that you do that here is there's a trick where you can multiply both of these by that x minus 1 denominator. Okay, and so the result of that, the numerator 1 times x minus 1 is x minus 1. In the denominator, what you end up with is you distribute this to those two terms there. in the first product, x minus 1 times 4 over x minus 1, that's actually going to cancel out the x minus 1 and leave us with a 4. And then we've got a plus 2 times x minus 1. Okay, that step's really the trickiest part of this. The rest of this is just cleaning up. Distribute the 2, so we get 4 plus 2x minus 2. And so we end up with x minus 1 over 2x plus 2. Or we could also say that's 2 times x plus 1. Okay, we can factor that 2 out. And the reason I do that, you'll see in just a second. But that's f of g here. That's that composite function. So going back to the original question, what's the domain of the composite function, f of g? Well, if you'll notice, 2 times x plus 1 in this denominator, that would mean that what x value doesn't work. That means x can't be negative 1, right? If you were to plug negative 1 into that denominator right there, it would break that fraction. So that's another exclusion we've got. And that's really what you need to do to finish finding the domain here. That's that second part of this. The first part is anything that doesn't work on the inside function needs to be excluded from your domain. The second part is, okay, go ahead and find the domain of that function. I'm sorry, go ahead and find that composite function, work it all the way down, and then when you get to the end, check and see, okay, are there any x values that don't work in this final piece right here? And in this case, x couldn't be negative 1. And so that's the other restriction that we have on our domain. So that's kind of the two things you check, the inside function and then the final result. Now the question we're left with there is, where did that minus 1 come from? You know, here at the end we just get this negative 1 that just appears that doesn't work in the composite function. But there's a reason negative 1 doesn't work. Okay? And that reason is, if you do g of negative 1, that's 4 over negative 1 minus 1, which is 4 over negative 2, which is negative 2. That's g of negative 1, so there's no problem there. We can do that. But if we go to then plug that into the f function, because that's what that composite function does, right? We go into the inside function first, and then that result goes to the outside function. What happens if we try to do f of negative 2? Don't we get a 0 in the denominator? Okay, which is a problem, right? So that negative 1 value doesn't have any problem with g of x. We can plug that into that g function, that inside function, no problem. But what happens is the result of that, once we plug it into the inside function, that result of negative 2 there actually breaks the outside function. Okay, and that's where that negative 1 comes from. So you don't really need to know that necessarily. Just know that you check any restrictions on the inside function. X can't be 1. And then you go to the composite function at the very end and say, okay, what x values don't work there? In this case, negative 1. And that's your domain. X can't be those two values. Okay, let's do this again. So we need to find f of g and f of f, and then state the domain of the composite function. So let's go ahead. We know we're going to need to know some exclusions here. So in this case, x can't be negative 2, and here x can't be positive 1, right? So we'll need those eventually. And actually for the first part, for f of g, we already know x can't be 1, right? because that's what the inside function is for f of g. So let's now go ahead and work and figure out, okay, what is f of g? Well, luckily we've already done that, right? Notice those are the same functions. So that's actually a repeat. We've already done part A. I didn't realize that. So let's go ahead and do part B. Let's back up. We know for part A, we already got our answer. That was, and then f of g, so that's the same functions. We got that to be x minus 1 over 2 times x plus 1. Okay, so let's do part B. This is f of f. So we're plugging the f function into itself. Whoops. So that's going to be f of 1 over x plus 2, which is 1 over x plus 2 plus 2. So when we plug this fraction into this x right here, that's what we get. Okay, here's that. What was an x is now 1 over x plus 2. And we said to fix this complex fraction, we multiply by that denominator, x plus 2. So we get the numerator is x plus 2. The denominator, again, there's some distributing that happens here. For the first product, 1 over x plus 2 times x plus 2 cancels out and just leaves us with a 1. And then we have 2 times x plus 2, which is 2x plus 4. So we get x plus 2 over 2x plus 5. So that's f of x. Not the easiest thing in the world, but hopefully you kind of followed through all that. So let's get the domain. So that's the first part of our answer. The second part is, what's the domain? To begin with, the inside function here is f of x. So what restrictions did we have there? X couldn't be negative 2. So we have that restriction. The other restriction comes from this guy right here. So what would cause that to be 0? So we set up that equation. If we solve that, we get negative 5 halves. So that's the other value that does not work in the composite function. Alrighty, that's that. Now earlier when we talked about these composite functions at the beginning of the section, I think I mentioned at some point that typically f of g and g of f are not the same. Okay, but that's not always the case. Sometimes they are. So for this example, it says show that f of g and g of f are both the same. They're equal. And not only that, they both equal x. So when you switch around f of g, g of f, you get the same result. It turns out to just be x. So we want to show that. The way we show that is we just work it out. So first, what's f of g of x? So g of x is a third times x plus 4. So then if we plug that into this x right here, this is the result. And I'm just mixed up my parentheses. Okay. So if we simplify this down, first 3 times a third, those just cancel out. 3 times a third cancels. So we're left with x plus 4 minus 4, and well, that's just, okay, these cancel, right? That's just x. So the first part, we've shown f of g, well, that's just x. Things cancel out. Now let's look at g of f. See if we can get the same result. F of x is 3x minus 4. If we plug that into g, get this right here, you'll notice the same sort of thing happens. Plus 4 and minus 4 are going to cancel out. And also a third times 3x is going to cancel out. We're just left with 1 times x, which is x. So sure enough, f of g and g of f are the same. Not only are they the same, they're both just x. And we have a special name for this, and we're going to get into it a little bit more in the next section, but this is what we call, go ahead and give it to you, these two functions are called inverse functions. And all that means is one function undoes the other function. Another example of an inverse function would be x squared and the square root of x. Those two functions are inverses of each other. One undoes the other. Okay? And that's going to be a lot of what we talk about in the next section. So we'll save that for then. The last little bit, I think we just have, yep. Disregard that homework that you just saw there. The last thing we've got here is finding the components of a composite function, and this is a calculus, kind of a calculus technique that if you do go on to take calculus, it might be something useful. You'll see something like this. It's basically what we just did, only backwards. Those previous problems, we would take two functions and put them together to form a composite function. For these examples, we're basically undoing that. We're taking a single function and breaking it into two components. And those two components basically make up what could be put together as a composite function. And an example of this is right here. This h of x is the square root of x plus 1. We could actually break that into two separate functions, f and g, where f of x is a square root function and g of x is an x plus 1 function. And the way that works is you start out doing, say that h of x is the same as that composite function. And then if you actually do f of g of x, okay, g of x is x plus 1, and then putting that inside f of x means you just take the square root of it, and you get the square root of x plus 1, which again, that is your h of x function. So you're finding two components of a composite function. What two functions could you put together as a composition to get that function you're given? So here's example 6. H of x is x squared plus 1 to the 50th power, and we want to know what two functions would work to make a composition that would be h of x. Now, a lot of times it's easy to think of this in terms of inside functions and outside functions. you'll notice on the inside we have x squared plus 1. So let's call that, now remember, for our f of g of x is the inside, right? So what's happening on the inside? That's the x squared plus 1. Okay, that's the inside piece. And then the outside piece is, you know, that whole thing being raised to the 50th power, and so we write that to be x to the 50th. So now if we do f of g of x here, that would be f of x squared plus 1, which would be x squared plus 1 to the 50th, right? And sure enough, that's what we started with. So this right here, those two components would be our answer. 7 is not quite as intuitive as 6 as far as inside and outside. You can also sort of think of this as steps. You know, if you were to plug an x value into this function, what would be the first step you would do? And that more or less makes up your inside function. So the first thing that happens when you plug in an x value here is you add 1 to it. So let's make that the inside function, x plus 1. And then the outside function, the second step, is you take that result and divide it into 1. So we could represent that by just saying 1 over x. So now if we do f of g of x, that's f of x plus 1, which is just 1 over x plus 1. So that checks out. That's our answer for this one. That wraps up 6.1. If you have any questions, please let me know.